This talk today will not be too technical. So the reason why we thought it could be helpful to compile this information is because there's a lot of things that we usually discuss, also not only with prospective customers, but also with people during their product development. And a lot of these questions that they usually come up and that we discuss. So we try to compile a lot of information of things that may be useful. It's a little bit like a list of things that, well, it's helpful to keep in mind when you develop optimization systems, and of course a little bit about how these architectures could look like and how this interacts with Gurobi technically and also from a licensing perspective. So we will take a very quick look at what it takes to solve business problems with mathematical optimization methods, and then we will take a perspective on optimization as a service. So in the sense that optimizing a business problem, solving an optimization model is really from a software engineering perspective, is really a service. And then we will take a look at different deployment situations, so scenarios, and also things that are helpful to consider when designing such systems. Then we take a quick look at the basic Gurobi licensing options, and of course some information how we, Gurobi, and especially the Gurobi support team can help you. So let's take a step back and take a very quick look of what we're actually trying to do. So the nice quote here is, whenever you have a business problem with a certain degree of complexity, always try MIP. So MIP is the technical term for mixed integer programming. So we usually, when we talk about business problems and their mathematical representation, we talk about MIPS because I'd say probably for 95% of our customers, this is the model type that they need to solve for their decision for their planning problems. And another reason is that MIP is I think we have, I don't know the exact list, but it's like 40 or 50 different industries where our customers work, and so different problems, and MIP is always the model type of choice, the ones that works really good, because it allows you to really reflect most of the things that you see in the real world. So whenever you do planning, the important part is not only you solve a single model, but usually you ask a lot of questions, like what if questions. So what if something changes in my planning problem, costs, prices, or some external things like demand, or you want to know what happens, so you want to optimize a certain future, a scenario, something that you can think of if you want to change something. So what is the impact, for example, for adding new production capacity? And the nice thing about MIP solving is it's an active area of research, but it has also been there for decades. So it's a wealth of techniques and then from very different domains. And the nice thing about it is if you solve such a model type, this is very robust to changes. So it's easy to change the model. And the methods still work very well. So you can modify actually a lot of it. You can modify the problem structure, add rules or change some logic or whatever, but you can also modify the data, like prices or costs or something. And of course, you can also change the perspective on your planning problems in terms of objectives or goals, like revenue or fairness or whatever your goal is for your planning problem. So that's why MIP is usually the right way to handle these problems. So usually these applications always look a little bit like this. This is what we call the optimization workflow. So you start with a problem instance, a decision problem, something that at some point of time has a problem that needs to be solved, some decision. And the first thing is usually that you select the data for this specific problem, and you put this into a model generator. So this is a software component that gets parameters and gets some data, and this actually transforms this into a model instance. So the mathematical representation of your actual current planning problem that you're trying to solve. And this model instance is the input to the solver, to Gurobi in this case. And so after the problem was solved, you retrieve the solutions, and then there's usually some post-processing, some analysis. So maybe you want to have a nice visualization of what you just calculated. And sometimes, or in many cases, you want to change something. Maybe you see, okay, good solution, but maybe we want to change something or analyze it a little bit or see what happens when you change certain things. So usually this is a cycle that starts from the beginning multiple times until you are, well, satisfied with the results. So Gurobi in this circle is actually a library. So from a software development perspective, it's really a library. So it's a high performance software component that can be embedded into applications. So it's like a third for most applications, like a third-party library that has a certain job to do. And in many cases, this is a black box. So in the front end, what people usually do is there's some magic button that says start optimization, and then some things happen, and then at some point of time the application says, okay, the result is now available. Because the end users of the applications, usually they are domain experts. They know very well about their specific problem, about their industry, about their company, and all the details of their problem. But they don't have, a lot of knowledge about mathematical optimization, and they don't have to. So for many applications, it makes sense to hide all this in the background so that the user only sees, okay, something is happening, and here's the result. So when you develop these kind of applications in this stage, you need an expert, a modeler. So this is the person that understands the business problem and creates the mathematical representation, the MIP model, or more precisely, the rules that you need to transform your data into this mathematical representation. And this is the thing that you need for a model generator. So this is the software component that actually does it. So given the data, given all the knowledge about how to create this mathematical model, then do this transformation. So this is a very important software component, and we will see in a minute, depending on the implementation, this generator can be at different places within your application. So in fact, we saw this circle. So we saw this point where the business problem is transformed into a mathematical representation, and it is solved. So optimization is really a service. And this is something that is also very popular in the development of modern software applications. So you try to divide. It's a little bit like the principle of separation of concerns. So dividing your application into loosely coupled or even decoupled functional unit. There's like this paradigm that says do one thing and do it well. And this is where you usually split all the functionality that you need into smaller pieces, which you call services. And solving MIP models, solving optimization problems, is in fact a service, because it provides a specific functional capability, the model solving, on defined input data, which is the model instance, and some representation within your computer. And then of course there is like an API and a well-defined way of how to submit things to the service and retrieve the results. So an application, that planning application, for example, is really a service client, and then it utilizes the optimization service. And sometimes this can also be on the same machine. So it's like a logical view on the software itself, or sometimes this can also be on a different machine. For example, a web service, where the whole thing happens somewhere else, maybe on the internet. And it's hard to say what's the right architecture for a specific application. That's usually where you have someone called a software architect. That's the person that decides which functionality is actually encapsulated into services. And so there are mainly, I would say, two types of services. So first of all, you can create some kind of general purpose service. So a service that accepts a model instance, so an instance of your mathematical models, and solves it and returns the results. and maybe also some additional functionality to monitor progress or control the running job. So this is very nice because it's really flexible. So if you have such a service available in your infrastructure, it means any application can connect to it and solve optimization models. The problem here is that the model building itself, so the model generator, is on the client side. So the person that develops the application, or the team that develops the application, actually has to know how to do that. And sometimes it's not so easy. So that's where we see domain-specific services. So sometimes a service is more for like a specific problem, like a well-defined problem type. And what happens is actually you move the model generator to the server side. So you provide the data and maybe some parameters to the client side. And what happens is everything else, so the model generation, solving, solution retrieval, post-processing, and whatever you need happens on the server side, and you get only back the results. Well, the nice thing about this is that most complexity is hidden in the background, and also the developer that uses this service does not need to know about mathematical optimization. But of course, it limits you to certain types of problem. So speaking of these general purpose services, if you want to use Gurobi to solve your optimization models, actually we already have an implementation that you can use. And this implementation is called Gurobi Compute Server. So this is an optimization service implementation, and it's also based on state-of-the-art web standards. So that's basically a web service. Of course, you could also use it locally, but yeah, it's already there. But of course, it's a general purpose service, so it requires you to build the model on the client side. So the nice thing about Compute Server is you don't have to need to implement the service yourself. In fact, if you use the Gurobi API, you don't even need to change your code. So that's the main advantage of using this service implementation, because you have a client-server separation within the product. So it's your client that builds the model, but everything else happens on the server, and you don't have to change the API. So it's transparent. So no need to change your code, for example. And that also means you can do this at a later stage. So for example, when you develop your application, you can work locally and also use the MIP solver on your local machine. But maybe later your application is deployed on some other machine, or you want to separate between your application server and some machine where Gurobi is running. You can always do this without changing your application. And one step further, it's not only that there's like another machine somewhere else that you can use as a server. Gurobi Compute Server actually also has the functionality of creating clusters of machines. So if you really need to scale this thing up, you can say, okay, I don't need 1 or 2 or 3 of these systems, but I can hide a cluster of Gurobi Compute servers behind the service interface. So that means the client still connects to the same machine, but in the background you have multiple machines that for example, balance the load of solving all these models. And for Gurobi Compute Server also has the nice property that it is completely integrated into the optimizer. So there is no additional software layer between client and server. And this is very nice because you don't need additional CPU or additional memory just to control the data flow and the communication between client and server. So let's talk about deployment. So the things to consider when you design a new application. And it's also a little bit about sizing. So what types of machines you need, how you want to design your overall application infrastructure, and of course the IT infrastructure in the background as well. So there are usually 3 interesting usage patterns that you could take a look at when you do this. So the first one is single-threaded versus multi-threaded. So when you solve optimization models, by default, you solve them on the same machine where your application is running. And of course, you try to make use of parallelism. So modern computers, they all have CPUs with multiple cores, so they can work on several things in parallel. And when Gurobi was developed, this was one of the key features, that this was developed right from the very beginning to exploit parallelism whenever possible on this hardware. So many models benefit from this, but some do not. Very small models or some special models. So those can also be solved single-threaded. So you take one thread, or which could be maybe one CPU core, and that's enough. It's quick, it works quite well. So in that case, maybe you can solve many of these models at the same time on the same machine. But it's always good to know if your model benefits from parallelism or not. Most MIP models do, but some do not, and in that case, you can just, for example, solve them only using a single thread. Then the question is, if you solve multiple models, can you do this in parallel, or do you have to do it sequentially? And that really depends on your problem. So for example, if you solve the same optimization model for different, let's say, regions, that means maybe you have 5 different regions, 5 different models, and you can solve them independently. In that case, you can solve them in parallel. So that it makes sense to say, okay, the total time for all regions should be as low as possible. So why not solve these models in possible on a proper hardware? But sometimes this is not possible. Sometimes the input for a model depends on the previous optimization run. So in that case, of course, you need to solve these models sequentially. And that is something to keep in mind, because this basically defines if you can create separate models, or if you really need to solve the models one after another, and each model is only created after the results of the previous optimization are available. And then there is a third pattern that is especially important for larger MIP models, which is single machine versus distributed. So for certain model types, it's very helpful to not only exploit parallelism on one machine, but to let multiple machines work on the same model at the same time. What actually happens is solving a MIP model actually means solving within a large search tree. And what Gurobi can do, it's integrated into the product, is distributed MIP. And distributed MIP means you have a bunch of machines, and you solve the same model with, and each machine works. So the machines work together on the same model. So this is something that can be very helpful, and it really depends on the model type whether you want to prepare your application or your IT infrastructure in the background to do this. So the next one is hardware. So that's a very common question. So people contact usually Gurobi support, and they say, okay, I need to invest into new hardware. Do you have a recommendation? How much memory do I need? Does it get faster when I add more memory? Is there a certain CPU model that you recommend, or something that you do not recommend? How much parallelism is good on a certain hardware? And it's not easy to answer these questions without actually taking a look at the model, because the model and the model structure really defines what algorithms are used to solve these models, and some benefit from parallelism, some benefit less, and of course it's always the case that models can slightly change. So what we usually do is we ask people to submit a set of models, and then we can run them in our environment, and we can give a hardware recommendation. I mean, we can give a general recommendation, something like, okay, you solve MIP models, they are a bit larger. So the best performance is usually go for a CPU with the fastest possible clock rate, and to have fast memory access, put 4 channels per CPU socket of the fastest available memory in your machine. And this is usually a very good start for MIP models. But to be more specific, it's always helpful to look at the model. So if you divide client and server, and you do this between different machines, of course, suddenly there is a new thing to consider, which is the network connection between the machines. So usually on a local network, this is not a problem. So what happens is the connection is fast, and the communication overhead, so the time that it takes to to send and receive the network messages is really not a problem. But sometimes it is, especially in situations where the connection between the two machines is a little bit less, let's say, local. In that case, for example, usually you have a higher latency. So the round trip time, the time that it takes for a message to go to the server and to get back with a response is a bit higher. It's usually not that much, so it can be like whatever, a few milliseconds. But still, if you do this quite often, so 1,000 times, then this sums up, and this can result in a delay that is long. And that means your total runtimes for your models degrade just because the network connection between the machines is a bottleneck. And this is also something that we see quite often at Gurobi support, so that people, for example, wonder how they can use our API to reduce the communication overhead with a network connection. So latency can become an issue. Sometimes it's also bandwidth, but usually for very large models. Of course, if you want to solve tons of gigabytes of data in your model in the cloud, that also takes some time. But latency is a real issue. So this is really something to consider when you design how your application infrastructure looks like. Then another question that we get is, so what programming language do you recommend? So of course, for new applications. So is there like a preferred programming language or something that you recommend or not recommend? Of course, there are very small differences between the different programming languages when it comes to Gurobi, but our general answer is no. Go with a programming language that works best for your application. And the reason is the API, so the software component that connects your programming language with Gurobi is really lightweight. We always say it's a very thin layer around the core API. So from our perspective, if you prefer Python, use Python. If you prefer Java, use Java. Or if you prefer .NET or whatever, use .NET. So go for whatever works best for you. Gurobi is really committed to all of these interfaces. So there is not a first or second class citizen language. We really support every language, and and the performance should be really the same, very close the same for all programming languages. Another question that we get quite frequently is, okay, I can choose between different operating systems. So do you recommend to use Linux or Windows or Mac, or even if you recommend, do you recommend Linux? Here are 3 different flavors of Linux. So which one works best? And the answer again is there is no recommendation. There may be very small differences between platforms, but the reason is that Gurobi code is compiled with different compilers for different platforms, and there can be very, very small differences, but it doesn't mean that you will that there is any significant performance difference between operating systems. So the answer here is as well, go for whatever it works best for you, pick the operating system of your choice, and that's it. There's one thing that is very nice here is if you do client-server separation using compute server, you actually don't have to use the same operating system on both ends. So what you can do is you can run a client machine on Windows and the server is running Linux, or vice versa. So that's possible, and that's another reason for this to maybe go with something like compute server, because it doesn't force you to use a specific operating system on both ends. So the next one is takes a little bit more time. So back in the days, I'd say most applications would run on bare metal machines. So there was no virtualization at all. Nowadays, in most cases, people run on virtual machines for many reasons, because it makes things much easier for the IT people. Virtual machines are very nice when it comes to flexible deployment on different physical hardware. It's also very nice for high availability. So if some physical hardware fails, you can just move the virtual machine without even noticing that there is a problem. So the system itself doesn't know exactly where it is running. That's hardware virtualization. So running virtual machines or multiple virtual machines on the same physical hardware. And the question is usually, okay, I'm solving optimization models. What's the impact? Does this slow things down? And the good news is no, it's not zero, but on modern CPU architectures, the overhead for hardware virtualization is really small because the CPUs they support it, and it may be a percent or 2 or 3. And in some situations maybe a bit more, but the impact is so small that that the benefits of using hardware virtualization usually are much better than just go for the pure hardware. So hardware virtualization works very well also with Gurobi. Then there is something called desktop virtualization, so a terminal server. So the idea is here you install your application on a certain machine, then people access the applications through something that is usually called a terminal server. So they can log into the system remotely and run the application from there. And from a Gurobi perspective, this is really easy because, okay, we are a local application, we run the machine, and we really don't care if users are sit in front of the machine or if they log in remotely. So from a Gurobi perspective, that really doesn't make any difference. So desktop virtualization is works very well. Also sometimes for deployment, because of course the IT people only have to install an application on a certain machine, and maintenance can be much easier in that case. And then there is a third type of virtualization that became incredibly popular in the last few years, which is operating system level virtualization. So containers. On containers, for those of you that don't know this concept, containers are an abstraction at the application layer. So that means you create small packages of softwares which are like self-contained, and they are isolated. So actually to run an application, you pick the right containers that you need, and then you maybe put them together through some service interface. And so the application mainly consists of decoupled functional units, and you put them together when you run the containers. And this is a very nice concept. It has many advantages because software development usually gets much easier. Deployment is much faster. And the main argument also for this kind of virtualization is that the overhead is much smaller compared to hardware virtualization. And another very nice property is that the environment is very well defined. So that's also something that is very nice. So the bottom line here is Gurobi can really be used at every virtualization level. For performance reasons, there's one important thing that you should always think about for any kind of virtualization. And this is the question, what's really happening on the physical hardware? Because virtualization usually means some part or some software system or some operating system running somewhere does not know what else is consuming the physical hardware resources. So one container has no idea what other containers are running on the system. Yeah, one virtual machine has no idea whether there are 2 or 3 or 4 or 5 other virtual machines running on the same hardware. And that means solving optimization models needs physical hardware power. So whatever virtualizations you use, make sure that it is available and that there is no other system that also consumes these resources, because then this would slow down the computations for your model, and this is something that you don't want. Sometimes we have customers that say on Mondays my model is fast, on Tuesdays it's very slow, and then after some time it turns out that on Tuesday there is some other virtual machine running that consumes much more computational power, and yeah, so that's really something to consider. So if you think about using virtualized environments, always ask for for the hardware behind it, and also if the access to this hardware is exclusive of if it's shared with other systems. So then another question is, okay, my application will solve optimization models. How long does it take? I mean, this is a very important question, because I mean, it means what can the users expect from it? Is it like a planning applications where you get your response immediately, or is it something that runs overnight, or is it like 5 minutes, 10 minutes? So how long does it take? And the answer is there is no other way to find out than to try it and to do benchmarking. And the main reason is that for MIP models, of course, you know the size of the models, you know how many variables you have, you know the variables types, and that can give you an indication of how long it may take. But in fact, it's hard, if not impossible, to really predict runtimes. So you need to measure, and that's something that should happen right from the beginning. So build models and measure how long it takes. Especially for this kind of performance estimate, so that you can say, okay, we know that like 10 minutes for our problems is good, and that it works, or maybe not, and maybe that allows you to work on the overall solution approach. But this is really important also to identify bottlenecks. So what takes time? Pre-processing, data processing, the model solving, the model generate, or maybe the post-processing. So in order to, if you remember the circle, so in order to make this whole process fast, you really need to look at what the bottlenecks are. And of course, it allows you to find the right hardware. So this is also something that we can do together. So feel free to contact the Gurobi support team, and let's take a look together at your models. So okay, so now we have talked about a lot of aspects that you need to consider when you develop these kind of applications and when you integrate Gurobi into these applications. Let's look at a few common scenarios how an application infrastructure can look like. So the first one is single machine deployment. So no client server separation, not multiple machines, just the application running on a machine and solving optimization models on the same machine. And in fact, many customers do this. So they don't use a client server separation or multiple machines. And this works pretty well in many cases. It doesn't mean that it can also, from a software engineering perspective, that the application contains like something that looks like a service, but everything happens locally. And there are many use cases where this works perfectly. For example, of course, for small models, for fast models. So if you solve models that solve within seconds or fractions of a second, this is usually, so the computational resources for this are usually very small compared to the rest. So why not run it on the same machine? There's something else that you can do. For example, you can solve models with low priority. So you say runtimes are not that important, so I just use the remaining capacity, so the idle time on the system, maybe from the operating system. This is something that can work quite well, because you say it doesn't matter when the model is finished. Can be 5 minutes, can be 10 minutes, and it's also a good use of the existing hardware. So why not do this? And there is something else that you can do. For example, if you do a strict hardware resource allocation, so you say, okay, let's say we have a CPU and we have like 8 physical cores. 2 physical cores are strictly for the application and 2 are strictly only for the optimization. Of course, if you do this, you don't have the problem that these both components slow down each other. And there are examples of applications where this works very well. So it's viable for many use cases, and especially if your usage patterns are very regular. It's good. So runtimes and performance are predictable, and it's perfectly fine to do this on the same machine. Also, if you know that there is no need to scale things up in the future. So even if you have to solve whatever 2 or 3 times the number of models, doesn't matter, because maybe they are very small. So it's perfectly fine to do this. But the next level is usually that you divide your application into a front end and a back end systems. And this is also a separation of hardware. So the front end, not from the user perspective. So there might be a user interface, which is another front end, but front end from an optimization perspective means it's the application server. So it's the server that runs the application on one or more dedicated machines. And in the back end, there is like the optimization server. So there is a machine where you solve optimization models in the back end, and we could call this the optimization server. And this has a few very nice properties. First of all, since both the application and the optimization require computational resources, of course, there is no concurrency here. So if you increase the load on the backend server, it doesn't affect the front-end server usually. Of course, it allows you to scale up because you can use one machine in the backend, or two or three, or scale things up. And this is very nice if you need to solve more models, or if you have more clients on your application server, or in these kind of scenarios. And of course, this is also very easy to implement using compute server. So you can start whatever with one backend machine and add a second one or a third one whenever you need it. And yes, that's but this is only an option. So of course, if you develop a front-end system and a back-end system, you can also do a service implementation on your own. In that case, you would install like a single machine license, for example, on the back-end server, and then write the communication layer yourself. So let's take a look at containerized applications. So we already had this on the slide with the operating system level virtualization. So the idea here is a containerized applications. All these software components, they share a common operating. So they run on the same operating system kernel. So no hardware virtualization, and deployment is really easy. Because from the outside you say, okay, I need a container from my database, a container for my web server, and a container for optimization maybe. And this is quite easy because you define this once, and then you just run your application. And this is very popular nowadays. So the most popular system to containerize applications is Docker for container management. And in many cases, if you need a system to do the orchestration, so to fire up the different containers and manage the system, that's usually done with Kubernetes. It's also very popular because you can do this on public cloud systems. And yeah, it's a very nice way to deploy applications. From a Gurobi perspective, actually running within this container, running within Docker is quite simple, because Gurobi is a library, and Gurobi sees, okay, I'm running on a 64-bit Linux system, so it works. That's not a problem. It's only a licensing thing, because of course the idea of a single machine license doesn't work with Docker. So the idea of a container is you can deploy it anywhere and with as many copies as you want. So you need a client license for Gurobi within a container. I have a separate slide for that. There are different options here, but it works quite well. So next one is cloud. So no own hardware, but you run your application on a private or on a public cloud. So there is an IT infrastructure that you usually rent or maybe pay by the hour. And in the last few years, a lot happened in this area. So public cloud providers made it incredibly easy to build the whole IT infrastructure in the cloud, not only the machines, but also the network. So you can say, okay, here's a virtual network and different components like the routers or even load balancing, and of course virtual machines, virtual computers. And the nice thing is here, no need to buy your own hardware. It's available within seconds, and also for most cloud providers, these machines work very well for optimization. Again, of course, the optimization needs two types of resources, which is CPU and memory. And if both are fast, then optimization usually works very well on these machines. And of course, you need to control machine termination. So in some cloud systems, you get like very cheap machines, but you have no guarantee how long they they run, for example, spot instances. So this, of course, does not work because an optimization has to finish. Bottom line, short one, all Gurobi licenses can be used in a cloud environment. So the only thing that you have to look at maybe sometimes is, of course, if you have a single machine license, it's important for the license key to work that the system looks similar the next time you start it. Otherwise, the license key mechanism may have some problems. But usually, it's not a problem to run on cloud machines. Yeah, quick look at licensing. Just the types of licenses that you need and how they fit into the different deployment strategies. So Gurobi has actually a very simple, transparent licensing system. The first license type that we have are single machine licenses, and there are 3 flavors, which is first the unlimited user license. So this allows you to run on a single machine with as many users as you want, and you can have as many concurrent runs of Gurobi at the same time as you want. So this is the traditional server license, but we don't call it a server license. It's just the unlimited use of Gurobi on a single machine. For some scenarios, we have a named user license. So this is not for automated things, but this is for individuals, for people that most of the time use their computer and run the optimization for themselves. And this is also with unlimited uses. It's a license for a single identifiable person. And of course, we have compute server. So compute server is in fact a single machine unlimited user license like the first one. But in addition, you can run Gurobi remote services. So you provide the ability for client machines to connect. And there is no limit. So the clients don't need licenses. They can just connect to your compute server and use and solve their models on this machine. The second type of license is floating. So there are some scenarios where you don't solve. So for a compute server, for example, you solve your model on a different systems. But in some scenarios, you want to solve your model on the local system, but you don't know what local is in any case. So this can float. So it's so floating licenses work by the number of users. So you can say, okay, I want like 10 different runs of Gurobi at the same time in parallel, but on different machines maybe. And in this case, you can use a floating license, and it works with a small license server, so that you contact the license server, you pull a token, and you can use this license wherever you want to. So next license type is Gurobi Cloud. So that we have a dedicated webinar for this, so I will just give a very brief look at this. Gurobi Cloud actually means you run Gurobi, in fact Gurobi compute servers, on some cloud machines, and you only pay for what you use. So the pricing is based on the machine uptime. So we fire up machines that you can use exclusively with certain hardware power. This is something that you define yourself. It's really easy to use. So you just install Gurobi on your local machine. You define your machine pool on the Cloud Manager, which is a web application. You download the license key, and you can use it from the client right away. It's really secure, so it's end-to-end encrypted between the client machine and the server machine. You can scale things up. So from a small low power server machine, we don't have low power. We have, let's say we have smaller and we have larger machines, and these and you can choose whatever works best for you, or you can even add more machines to your machine pool. And if your cloud application actually runs maybe in the same data center or maybe in the same region, you can also choose where exactly your cloud machines should be located. And everything can be controlled through the REST API. So in that case, all the clients, they don't need their own license. The license happens only on the cloud side. So whenever there are machines up and running, you can connect from any client around the world using this specific license key. It's like the password to access these machines. So let's go back to Docker. So single machine licenses don't work with Docker. That's just a different concept, but you can use all other licenses for this. So compute server works. So the model is generated within the container, but it's solved on the compute server. Same for the instant cloud. It's just that you don't connect to your own compute server, but you connect to a cloud machine. But if you want to, you can also use floating licenses so that you solve the model within your container. Again, the same question here. Where do you have the hardware resources? If they are on the physical hardware that runs your container, that's fine. You can solve the model within the container. But in many cases, maybe you want to solve the model outside of your container, and this is where you can use compute server or instant cloud. So a lot of things to consider. Last point is support. So you don't have to think of this all by yourself. So if you're in the process of designing your application, actually this is something that we do every day with our customers and prospective customers. So if you want to, we can discuss. So we can take a look at your architecture and discuss whether you need to change it, or if it works very well for what you are trying to do. And we can not only assist you on the technical level, we can also do benchmarking on our machines, discuss architecture, and also give hardware recommendations. So we can be like a counterpart for the planning of your application architecture. So just let us know if we can assist you with that. And last but not least, we have touched a lot of topics in this webinar, but only on the surface. So it's like general knowledge, things that are important to think about when you design these kind of applications. But of course, we have a much more detailed information about all of these topics. So I'd like to point you to our website. So there is a section for seminars and videos and the recordings of our webinars. And we have very different webinars for example, for the business case. So for the question, is optimization so something that is helpful for my problem or for my organization, and how could a business case look like? We have more technical webinars, something like latest developments on the product, or more details, especially technical details about compute server and the cloud, and of course model building, modeling, and of course model tuning. So this is something where we have like series of webinars. So feel free to go there. It's public. You can log in and take a look right away.